Uh, so this is the second class out of this course, and then you know the recently the COVID-19 situation is very severe, and then I hope for every student stays healthy and then keep safe. But unfortunately, some students email me that they are tested positive. So, but it's very, so actually in the first class, I ask you that if you are tested positive, email me immediately, because this is very important for other students' health, and then also it's critical for how to manage this course during the spring semester. So I appreciate those students who not email me about some result of the COVID-19 test. Okay. So yeah. So in the okay, I will start today's class. So in the previous class, we learned that there are many different kinds of computer systems in our world. Actually, this course is the computer architecture course. So we will learn about the computer systems or computer hardware. And then actually in the syllabus, I also explain which items will be taught in this course. So we will learn about the actually the basic concept of computer architecture, also including instruction set architecture and the pipelining. That is the basic of process architecture. Also, we will learn about the memory hierarchy. And then I said that these three topics are highlight of this course. So, okay, so if you take this course, then you need to learn about the instruction set architecture and pipelining and memory systems. Okay, so in the previous class, so I saw these slides. So as you can see, there are many different kinds of computer systems. Also, the shapes are different. So also the figures are different. And then, as you know, the performance and then cost are different. So actually, we choose these different kinds of computer systems based on our purpose. That means that our usage model. So, for example, we use our smartphone for mobile computing system. So we can carry our smartphone. Also, we can see the display of the smartphone whenever we want. Okay, but what is important for our smartphone hardware? So energy consumption or some power consumption is the critical factor of our smartphones. Okay, why? The power source of the smartphone is battery. So actually, this battery has the limited capacity. So in order to run our applications on our smartphones, then the battery needs to have enough the power sources like electrons actually. So it's energy consumption means that energy consumption is the amount of power consumed during the some execution time. So if our smartphone consumes much energy, then the battery lifetime will be very short. So that means we cannot use our smartphone when we want to use because the battery is empty. So that's why for the smartphone or mobile computer system, energy consumption is the critical factor of the computer hardware. So then like this, we learned the different classes of computer systems like personal computers, like desktop or laptop computers, and then server computer systems. So I explained that many other people use server computers concurrently. So for the server computers, the performance, also the reliability is the critical factors. Okay. Also, supercomputers, embedded computers, such like mobile computers. So there are different kinds of computer hardware. Also, so I saw these slides. Also, there are different architectures. So like CPU and GPU. So I also explain about this. I briefly. So actually, I believe you don't know about the detailed inside of the CPU or GPU processors. So because this is the undergraduate course. So, but CPU and GPU have different architectures. So I mentioned architectures. So that means that the structure and components inside of this CPU and GPU are different. So CPUs and GPUs have different components or different structures or different size of memories and so on. So that means so actually the CPUs or GPUs are processors, and then in the computer system, the processor is like a brain of the computer systems, but architectures are different. Also, I believe if you are interested in CPU processors, then I believe you have heard about some different architecture name of the Intel CPUs, like core architecture, or Broadwell, Haswell, Skylake, Ice Lake, or Elder Lake. So that is actually the brand name. It's a brand name of the Intel CPU families, but these different brand name, or actually it's the name of the architecture. So that means that it's the same Intel CPUs, and then these Intel CPUs can run the same applications, but inside of these different Intel CPU architectures, the structure, also the hardware components are different, okay? And then these different hardware structures or architectures or different components decide performance, cost, or other factors of the computer systems, like energy consumption or power consumption, okay? So computer architecture decides performance, cost of the computer systems. So then how the performance of a computer system is determined. So you can think like this. So if we invest more money for our computer systems, like if we buy very expensive smartphones, then we expect that, oh, our smartphone is very good. So we can run the same program very fast. Then how this performance of our application, then the application of the smartphone is determined. We just pay more money. Then what is different under the application of the smartphone? So actually, these factors decide the performance of our applications. Like, oh, colors. So algorithm. So algorithm is just the software, and algorithm is some theory or some methodology that decides the answer of our some questions or our inputs. So algorithm also decides the performance of our software. Also, program language, compiler, or architecture. Architecture means that instruction set architecture. So it's program language. If the same application is written in Python or C, then the Python is easy for writing a code, but the speed of the Python is extremely slower than than C. Okay, so you can search the C versus Python in the Google, then you can find that some different factors of by C or Python programming. But so you may find some different graph that shows the execution time of the matrix multiplications. So it's the same matrix multiplication application. So it's the same matrix multiplication, and then algorithm is the same, but this same algorithm can be written in C or Python. And then compiled, and then if this program is compiled and then executed on the same computer systems, like same computer hardware, the performance actually different. C is much faster than the Python. So program language also determines the performance of our computer application. Okay, like a computer system actually. And then compiler. So I mentioned compile. So compile means that our program need to be translated into the machine languages. Okay, so you will learn about this machine languages in the chapter 2. So compiler options also the compiler techniques decides the performance of our applications. And architecture. Architecture means the instruction set architecture. That means that you can compile your same program with the ARM architecture or x86 architectures. So if the different architectures are applied to the same application, the performance can be different. Okay. Also, hardware, processor, and memory systems. So these are very tightly related to the hardware. So you may consider the different CPU families such as the i3, i5, or i7. So, the i7 and recently i9. So i9 is the most expensive core in the Intel Core architecture. And the i3 is cheap. It's cheaper than i7. So if we use the different process architecture, then performance can be also different. And the memory system. So you may consider the size of the main memory. My smartphone has 2 GB of the main memory. And then another people may say, oh, my smartphone has 6 GB of main memory. So which one is better? If the smartphone has larger size of main memory, then we can expect that, oh, this smartphone is better. And then the performance of the smartphone is higher than the other smartphone that has smaller size of main memory. So these are related to hardware architecture. And then I/O system. What is I/O system? I/O means input and output. So actually, our computer systems are connected to outside the world. Okay, so I explained that the CPUs or processors are brains of computer systems, but our computer systems are also connected to the outer world or real world via input and output interfaces. So what are the examples of I/O systems, such as display, like some monitors, and keyboard, mice, and networks. So also these I/O systems determine performance of entire computer systems. Okay, so how about network? So if the network speed is very slow, and then recently most of the our mobile phones are connected to cloud systems. So if the network speed is very slow, then we can say that, oh, our smartphone is very slow. Actually, it's the same hardware, but network speed is different. That means slow. So this slow network speed determines the entire performance of our smartphone systems. Okay. So actually, if we consider about the performance in the computer systems, we need to consider these different factors, such as algorithms, software, the program language, compiler, and hardware and I/O systems. Okay. So computer architecture. So and again, computer architecture. So why need to learn? So why do you select to take? Why did you select to take this course? Why need to learn? Because this is mandatory course of the computer engineering department. So I think that's the main reason of the many students. But why do we need to this computer architecture course? And then why is this computer architecture course mandatory course in the computer engineering? So computer architecture course is the basic step to understand computer systems or computer hardware. So you know, everyone knows that computer software runs on the computer hardware. And then in order to understand about the performance of our computer system or performance of our software or applications, because you are not coder, you are a computer engineer. Okay, so can you understand? You are not a coder. So what is coder? The coder is just write a code, but you are an engineer. So you are working on computer systems or computer software, computer hardware. So computer architecture is a basic step. So it's a baseline step to understand how computer works. Okay, and it's very critical for the computer engineering students also. So if you try to measure the computer software, then it's very critical. Okay, why? Everyone needs better computer systems. Okay, what is the better computer? What is a better computer system? Computer systems that have higher performance, that means it's a fast computer system. Also, computer systems that consume lower cost. And then the main cost of the computer system is the electric power. So that means that the power consumption or energy consumption. Okay, so low energy consumption. Because low energy cost is very critical. So if we want to build better computer systems, then for higher performance or low energy consumption, then you need to learn, you need to understand how computer hardware works. Then another question is, then computer architecture is only required for hardware engineers? Definitely no, because it's also critical for better software design. So what is the better software? So, and then you may, so many people say like this. So it's the same game. So it's the same game application, but so you mean, so that means the graphics requirement or graphic quality of this game application maybe it's similar, but performance, like number of frames per second, or some quality of the small object may be different. Why? Some software is optimized for some specific computer hardware, but some software is not optimized. Do you understand? So optimization means that the same software, but some software is optimized for the computer hardware, then we can get better performance, better quality, or some better services. Okay. So computer architecture knowledge is required for building better software. Okay. Also, domain-specific software. So what does that mean? Traditional computer systems mean the general purpose CPU and then the general purpose application. So normal application runs on general purpose processors. That is the traditional view of the computer systems. But recently, as you know, machine learning applications or AI applications are actually performance is very critical for these type of applications. And then, you know, these applications usually run on GPUs. It is because the parallel processing or parallel execution is very critical for some types of applications, such as neural networks or machine learning applications. So these applications need to be run on parallel processors like GPUs. Then GPU, as you know, GPU means G means graphics. It's not central, it's a graphics. So which means GPUs are designed for graphics application. It's the specific purpose of the specific purpose processor, not general purpose. So now to utilize the hardware of GPUs, then you need to understand how GPUs work and then how softwares or GPU applications run on these GPU architectures. Okay, so these type of applications are called domain-specific software because it's a graphics domain. So traditionally, the computer system, like computer, is designed for run general purpose application. But recently, we focus on the domain-specific applications or domain-specific software because the performance is very critical. Why GPUs are used for these type of applications? Then we need to run our machine learning applications very fast. If these applications are run on our CPUs, okay, for example, CPUs, then it will be very, very slow. But we don't want, everyone does not want slow computer systems. So these applications are run on the GPUs. Is domain some specific processors, okay? And hardware software co-design. So it's also very important because so some software is just actually coder does like a code. So coder just knows how to program, like how to write a code, okay? Just knows the syntax. But as a computer engineering students, you need to understand how computer works. Then we can optimize our applications under some specific hardware or some general or some computer systems. So this approach is called the hardware software co-design. So actually for the embedded computer systems, hardwares are different. So that means so embedded computer system is that the computer processors are deployed to TV systems or some some AI speakers, like wearable watch, like a smart watch. So actually the hardware purpose is different. That means that the purpose of some hardware or some system is very specific. Actually, in order to optimize the cost for this system, hardware software co-design is very critical, because actually the available resources in this system is limited, and then but everyone wants the very high performance. So in order to maximize the performance of this system, then hardware software co-design is required. Okay, so that's why we need to understand hardware of the computer system. That means that, so why do we need to learn computer architecture? Okay, so I explain about what we will learn in this course. Okay, so I believe the goal, students need to understand the goal of the course in the first time of the course, because the student so motivation is very important. Okay, it's another topic. It's abstraction. So I explained about the abstraction in the previous class. Is a very briefly. So abstraction is the very important concept in computer science or computer engineering. So what is the abstraction? So abstraction means that so abstraction means making complex systems or making some complex devices with some simple aspect. So that means that, so I will explain, I will take an example of the abstraction in our real world. Okay, so actually the abstraction means they make complex things simple. Okay, so these are the examples of abstraction in our real world. So what is this photo? It's a driver, and then this is the abstraction layer. So, in order to drive a car, then which knowledge is required? So actually, everyone knows a car is a very complex system, right? So there are many components inside of our car, and then actually the mechanism and then some mechanical connection between these components are very complex. But in order to drive a car or in order to use a car, we just need a knowledge of how to use handle and then how to use a brake. So actually it's the basic knowledge required for driving a car. So this is the abstraction layer. Why? Actually, the inside of the car, there are many complex components such as engines or brake systems, but you don't need to know about how engine works or how brake system works inside of your car. The required knowledge is the how to use handle or brake. That's it. So what does it mean? actually the system is very complex. The system is very complicated, but we don't need to know the entire things inside of this system because we can understand everything because system is very complex. But this complex system is hidden. It's a hidden under the layer. We just understand some interfaces. So these engines or operating systems are inside of our car. It's an under layer, but upper layer, there is a handle and there are pedals, like brake pedals as an acceleration pedals. So those are interface that connects a driver and systems, complex systems inside of our car. Okay, so this is an example of abstraction. Okay, so in the computer system, actually, so we just see the hardware of the computer system, and then we learn applications on this computer hardware. But actually, the computer systems are composed of many layers. Okay, so if you took the digital logic design course and then with this book, like digital design and computer architecture book, then you may be familiar with this figure. So these are the layers inside of our computer systems. And then, so as also you can find the definition of abstraction, like it's a 추상화. So definition of abstraction is that is hiding details when they aren't important. So that means this underlayer is very complex to understand, but we just understand the required things. And then these required things actually do this. This is called the interfaces. And the interfaces are very, very simple compared to the inside of layer. Okay. Okay. So as you can see in this figure, that you can find many layers inside of our computer systems. So actually these are software layer, then these are hardware layers. So what is the top layer of our computer system? So user applications. Okay, so what is a user application? It's a normal application actually. So we can use in the internet browser or office applications, or you can use game applications. Then those applications run on the top layer of the computer system. So we actually communicate with these user applications. Actually, we use these applications directly. So this is the topmost layer of the computer system application. And then under this application, there is another layer, another software layer called operating systems. So what are the operating systems? Popular operating systems like Linux or Windows. So actually, everyone knows, or Android. So everyone knows our applications on operating systems. So like the browser runs on Windows or Linux operating systems. Okay. So these operating systems are required by operating systems are also interfaces between normal software and hardware. Okay. The operating systems manage the hardware components or computer hardware, and then operating systems also allocate the hardware resources to normal application. Okay, so manage the execution of normal applications. Okay, and then under the operating system, there is an architecture layer here. So usually this architecture layer is the instruction set architecture and other components, okay, like computer system architecture. So I will explain about the computer system architecture later. And then under this layer, you can find the microarchitecture. So microarchitecture means the architecture of processor, like i5, or like the Broadwell, Haswell, Ice Lake, Elder Lake. Those are brand name of the microarchitecture. Okay, so microarchitecture just means the architecture of the processor. And then, so these two layers are area of computer architecture, like architecture, like system architecture and microarchitecture. Okay, so we will learn about these two layers in this course. And then under this architecture layer, it's very complex. Also, it's very complex. There are different kinds of layers like logic layers, digital circuit layers, analog circuit layers, devices, and physics, like how electron works, how positive particles works. It's an area of the physics. And then device like just how CMOS work, how CMOS is generated, or how CMOS transistors are built on the silicon wafers. So these are the area of devices in the analog circuit, and then connected the CMOS transistors, and then build some analog components. That is the area of analog circuits, then digital circuits, and then logic. Logic means some basic gate logics or multipliers, adders, something like that. So actually these logic layers or digital circuit layers are are covered by digital logic design course. Okay. So we will cover these two layers, architecture layer and then microarchitecture layer. Also, abstraction is a very important concept in the computer systems. So please remember the definition of abstraction. Then how can you understand the architecture of or process architecture? This slide shows the diphoto of Intel i7, Intel i7 processor. So how can you understand the some architecture or structure of Intel i7? So what can you see? Actually, yeah, so this is a Zoom course, so it's not hard to get answers from student. So we can see many transistors were, yeah, many transistors in this photo, but we cannot understand how i7 works. And then also with this photo, so we can see many, like billions of transistors in this photo, but we cannot get any information. We can see, oh, this photo is very beautiful, and that's it. We cannot get any information about the Intel i7 processor with this photo. Then how can you understand the processor of or processor architecture of Intel i7 CPU. So different level of the abstraction. So what is added in this photo? So you can find that, oh, this part is memory controller. This is the CPU core, or this is interconnection. This is the some IO components or system agent. Like, and then also we can, oh, this is the GPUs, like Intel embedded GPUs. So, and then also we can find the level 3 caches, like here. So if we see this photo, we can get the brief structure, a brief component inside of Intel i7 CPU. Okay, so what can we get? What is the information we can get from this photo? So we can know, oh, this i7 processor has 4 cores, 4 CPU cores. Also, this i7 CPU has GPU part here, so we can, if without this CPU, then we can use display without GPUs. Also, these CPUs are connected via interconnection bus, and level 3 caches are shared caches. Level 3 cache is shared by these 4 cores. So those are, this is information from this photo. What is different? So if we see just this photo, oh, there are many transistors and it's beautiful. That's it. But with this photo, then we can get some information from of Intel i7 processor. This is another example of abstraction. With this entire photo, we just see the very complex transistor systems, like very complex digital systems, but it's very hard to understand. But with this some rectangular view, like the components are rectangles are overlapped over the die photo, so we can get some information of Intel i7. It's very simplified, but we can slightly understand about the Intel i7 processor. Okay, it's a very complex system, but it's a simplified system. And with the simplified system, we can understand about the some system object. So why do we learn computer architecture? So actually in the first class, I mentioned, so the goal of this course is to understand computer systems with an abstract level. Okay, it's a abstracted level, abstracted view. So we learn about the computer systems with architectural view. Okay, it's architectural view. So what is the architectural view? This is an example of architectural view of Intel i7. It's the same processor. So can you see? So we cannot see any transistors in this figure. You can see some rectangles and then some arrows, like some lines that connect different rectangles. So actually, one rectangle represents a component. Okay, how do you component? And then what does this line mean? What does this line represent? Line represent the movement of data or control signals. So data for control signals. So what can we understand from this architectural view of the i7 processor? So I think, this architecture is a rather complex. We will not learn about the i7 architecture in this course. We will learn about the very simple pipeline processor architecture. So if you do not understand about this figure, just ignore. It's okay. So if we see this figure, then we can find, oh, this is the decoder. Okay, or this is the instruction cache. So actually the instructions are stored in this instruction cache, and the instruction is read from this instruction cache. Oh, instruction is delivered to the decoder. And then with this decoder, the different kinds of instructions are decoded and then executed by different kinds of execution engines. So this is an example of architectural view. So what does that mean? Actually, these components like cache, some TLB, what is this? It's some ALU. So actually, Intel calls these execution engines execution functional units. So these are designed using logic designs, like here. Okay. And then simple logic designs are also designed from digital circuits. So some logics or designs are not seen in this figure. We just see some components, and then components are just connected each other. But with this architectural view, we can understand how the entire this processor, actually this is the processor core, how process core is organized using different components. Okay. So digital design is a kind of low layer. So actually digital design just focus on each component. So for example, with the digital design, we can focus on how to design adder, how to design multiplier, how to design decoders. But with this, different components are assembled and then connected to each other. Then we can also build the upper architecture, like some upper architectural view of the system. See? So these are simplified, but with this simplified view, then we can understand how the core processors are designed and organized. Okay, this is an architectural view. And then this is the architectural level, architectural abstraction level. So we will learn about the computer systems like this architectural view. Okay, so this is another example of the architectural view of our computer systems. Like actually, this figure shows the only 3 layers like software, operating system, and hardware. So I already explained about these different layers in our computer system, so I will skip this. But we need to know how programs are executed in our computer systems. Okay? Why? Yeah, so we are a computer engineer, not coder. So actually, we write our program with a program language, and then like C or Python. Actually, these program languages are called high-level languages. High-level languages. So why are these languages called high-level languages? It's a high level. So if there is a high-level language, then there can be low-level language. What's the low-level language? So actually, the high level, so we can easily understand high-level languages. So that means we can easily understand Python, syntax of Pythons, or C, or some other languages such as Swift, Go, Java, so Perl, different languages. Why? These languages are very similar to our natural languages. Actually, English. You know, the syntaxes of C or Python come from English words like what's that? So for, while, some print f. So actually, these are English words. So high-level languages are very similar to our natural languages, but so we need to learn about the syntaxes of these languages, but we can easily learn or we can easily understand how to use these programming languages. Okay, but computer hardware cannot understand these high-level languages. So actually, the computer hardware is a digital systems. And then these systems can just understand digital signals like 1 or 0. So these 1 or 0 signals, digital signals, are electric signals, right? 1 means it's a high voltage, and then 0 means it's low voltage or ground. Computer hardware can only understand digital signals, that means electric signals. So between these high-level languages and digital signals, this gap is very long. We cannot understand electric signals like 1 0 0 0 0 1 1 1 1 1. We can understand. And then computers cannot understand our natural languages or high-level languages. So how can we use our computer systems? So if languages are different, we need a translator. So just in the same way, high-level languages should be translated into machine languages like digital signals. Okay. So that's why we need these translators called compilers. So let's see how the high-level languages are translated into digital signals or some. So this is an example code of high-level code written in high-level languages. So this code is written in C. So if we see this code, there are some English words like swap, integer, temp data. So we can understand how this program works. And then by compiler, this high-level code, so this programming code is translated into the assembler or assembly language. So this is an example code of the assembly language. So if we just see that this assembly commands or instructions, this is this is an English letters. These are English letters. Oh, it's also familiar. It's not digital signals. And then, but it's not easy to understand how code works with this assembly language. So by compiler, high-level languages are compiled, so translated into assembly code. And then actually the instruction set architecture defines the instructions. So that means the assembly instructions used by some instructions, some computer hardware. Okay. So these high-level codes are compiled, and that means translated into assembly codes like this. And these assembly codes are also translated into digital data. Then each bit of the digital data can only have 1 and 0. And I also explained that 1 means high voltage, and then 0 means low voltage. So each line of assembly code is translated into the digital data like this. Okay, and then actually this data is stored inside of the computer system, and then computer system reads this digital data and then execute the instruction. Okay, so if we see this code, this data, you can understand. It's just a group of ones and zeros. If we study about some instruction set architecture, then we can understand the assembly code, but it's not easy. Actually, every line of assembly code represents instruction. Okay, and then this instruction is translated into the line of this digital data one by one. So I don't know if this is proof, but SLLI, X6, X11, and 3 is translated into this line. So assembly is very similar to the machine languages. And then actually the machine language has only a bit data, like digital data, like 1 or 0 zeros. But this assembly code is one-to-one map to this machine language code, machine language line. Okay, that's how the programs are translated into the machine language. Okay. And I briefly explain about some components of the computer systems. So actually, you know, if you just open your desktop computer your desktop computer case, then you can find the many components, many different components such as CPUs, like storage devices such as SSDs or HDDs. Also, you can find the main memory as a DRAM. So you can find some power supplies or main board, blah, blah, blah. So actually, computer system is composed of many different components. Okay, like some memory devices, storage devices, network, and I/O systems, I/O devices. So those are components of computer systems. So this figure shows the photo of the main board, but this main board is a very old main board. It's not, so as you can see, you can find the AGP slot. So usually we use the PCIe slots for GPUs, but the old previously we use AGP slots. But I just show this photo of the main board to show, so there are many components. It's a very complex systems. So as you can see, the CPUs will be equipped under this CPU slot, and then main memory, like a DRAM, is connected to DIMM slots on the main board. Also, we can find that, oh, this is the main board chipset, and then some peripherals are connected to CPUs via some slots. Actually, recently we used the PCIe slot, but in the previous generation, we used the different kinds of slots, such as the AGP. So many components are connected. It's also complex. It's just the photo. It's not easy to understand, but we can understand how computer systems are organized using this simplified view. It's also kind of abstraction. So this is the example view of the old computer systems, not modern computer systems. So as you can see, this is the CPU, okay, so CPU, and then CPU is connected to memory via memory bus, okay, so memory bus is here, and then also CPUs are connected to graphics GPU using via general I/O bus like PCIe. This is the old system. This is an old system. Also, many I/O devices are very slow, so we don't need to use the very fast interconnection for these I/O devices. I mean, mice are very slow, keyboards are very slow compared to the GPUs or memory components. So we can, for these slow I/O devices, we can use very slow bus, like peripheral I/O buses. So this is some abstracted view of the computer systems. But recently, the modern computer system is a little bit different. So in the old computer systems, there is north bridge here and then south bridge here. So north bridge is another chip on the motherboard. And then this north bridge manages the data transfers between CPU and memory. And then south bridge also manages the communications between many different peripherals, like here, the slow components. But recently, the north bridge part is integrated in CPU. So CPUs are directly connected to memory and GPUs. Why? We need very high bandwidth from GPUs and main memory. So if chip is located outside of a processor, then bandwidth is decreased. So we cannot use many pins if the chips are separated each other. Then if this chip count are decreased, then bandwidth is also decreased. So modern computer systems integrate this nose bridge part inside of the CPU to support the very high bandwidth data transfers between GPUs and memory. How are the I/O devices? I/O devices are still slow, so these slow devices are managed by I/O chips. It's the mainboard chips. Okay, this is some overall view of modern computer systems. So if you find some motherboard chipset information from internet, then you can find some similar figures like this. So this figure explains how CPUs is a Intel 8th generation Intel Core processor. CPUs are connected to this system motherboard chipset, and then how motherboard chipsets are connected to other I/O devices, and also this CPU chip is directly connected to graphics like GPUs and memories, like DRAMs. So that is the overall view of our computer systems. Okay. And then technology. So we have only 7 minutes until the end of today's class. So I also covered this part. You know, the computer processors such as Intel CPU or NVIDIA GPUs are actually chip. So that means the chip means, so recently the chip is very critical for the industry of each nation. So what is chip? What are chips? It's very, actually the chips are semiconductor devices. That means 반도체 in Korean. So CPUs the GPUs are actually product of semiconductor technology. So that means the performance of these processors are determined by determined by technology. So that means that if we can use very fast transistor, then the performance of our CPUs or GPUs can be increased. So what is the fast transistors? What are the fast transistors? Fast transistors means that, so actually the transistor handles the electric signals like from 0 to 1 or 1 to 0. And then I explained that 0 means the ground or low voltage, and then 1 means the high voltage. So if the signal is changed, then the electric signals or electric voltage swings from high to low or low to high. But after some delay, after some time, the electric signals changes from low to high or high to low. So I mentioned some delay. So if we can reduce this delay, that means this transistor is faster. So advanced semiconductor technology means it's very fast transistor and then fast transistor means that electric signals change quickly, very quickly. Then how can we make fast transistors? If the transistor size shrinks, that means that the size of a transistor is reduced, then we can make fast transistors. Okay. So also, what is the benefit of these smaller transistors? If we can make smaller transistors, then that means within the same area, we can include more transistors. So this is the hardware resources. So if more transistors are included in the same area, then we can implement more functions. That means it's a better processor. Okay. So the transistor semiconductor technology is advanced. So that means that the size of transistor is decreased, so reduced. So then usually this size of a transistor is determined by channel width, and then so it's the channel width, and then usually we call this channel width as technology node. And then I believe you have heard about some 10 nanometer technology or 5 nanometer technology. 5 nanometer technology is developed by TSMC or Samsung. 10 nanometer technology is developed by Intel. So I believe some of you have heard about this terminology. So in this technology node means the width of the CMOS transistor. That means if this number is decreased, then that means the size of a transistor is also reduced. So and then, as I said, if we can use the smaller transistor, then we can build better processors. That means faster processors. So as this semiconductor technology advances, then also the performance and then performance of the processor also increases, and then the cost is reduced because the size is reduced. So as you can see, this is some advanced history of the semiconductor. Then actually the first semiconductor is the vacuum tube, and it was invented in 1951, and then transistors are invented. And then so as you can see, we can compare the relative performance per cost. So that means the performance is increased very dramatically because the semiconductor technology have advanced very dramatically. Okay. Okay. So, and then this slide shows how the semiconductor chips are manufactured from the silicon. So, but it's not important actually. Actually the silicon is the semiconductor devices, and then firstly it is made from sand, and then actually firstly we make the silicon ingot. It's just the cylinder of the silicon, and then we just cut the silicon, and then we can just make the blank wafers. And then actually the process chips are fabricated on these blank wafers like this. So this is the photo of the i7, and then you can find that. So this is a single die. A single die is a die. Many dies are fabricated on the surface of a wafer. So, and then this is the recent chip, the dipole of the recent Intel Core 10th generation core. So what is different? Actually, the wafer size is the same. The wafer diameter is the same, but I mean, the technology node is different. So that means on the same wafer size, this wafer can produce 500 chips, but these wafers can produce 280 chips. Why? Because of the technology nodes are different. Okay, so better transistor or better advanced semiconductor technology leads the development of the higher performance processors. Okay, so that's why the silicon technology is very critical for the CPU or processor industry. Okay, so I will stop here. So sorry for the late. So any questions? Okay, so if you have any questions, you can ask the question after the class. So okay, so thank you for listening, and then thank you for your attention. And then see you in the so actually there will be no class on Wednesday because the Wednesday is the election day. But as I promised, I will record the lecture video and then I'll post the lecture video on the YouTube. Okay. Okay. Thank you, everyone, and see you